Now we're going to be moving into sample size. Now, sometimes we might have a sample that is really small, that doesn't give us the information that we need. So there is a minimum amount of sample that we can have. And that's what we're going to be talking about today. So I remember we talked about a formula before. Let me just zoom in here. Remember the formula X crossbar plus or minus our C scored times our standard deviation divided by the square root of n. Remember that formula. A standard deviation, we use S for standard deviation of a sample. We use sigma if we're looking at the population. Now, in reality, this part right here, let me highlight it or let me circle it. This was our error, right? How far off we were from our mean. We call that an error, right? How far off we were from the mean. So we found a score, we found an interval, right? Usually in the interval, right? The interval we meant there were two values and we said it's in between those two values. Right of the center was the average. But again, this is what we call our error. So let me just come over and say, I'm going to use SE for error. SE is going to be our sampling error. Our sampling error, it is equal to our C scored multiplied, I'm going to use sigma. We could use S if we're looking at sample, but I'm going to use sigma divided by the square root of n. That was our error. Right? We went how far up from our mean, how far down from the mean. So that was technically the error. Now I'm going to use this value. I'm going to use this formula or this equation to be able to solve for my sample, to basically solve for n. Okay, I just said solve for n. So wouldn't it be nice to have an equation that tells me that n equals something? Okay, yeah. So for my next step, if I'm looking at n has the square root. Okay, I want a formula that has n by itself. Again, I want to come up with a formula to be able to solve for the sample. I don't want square root, so how do I get rid of a square root? I know addition and subtraction undo each other. Multiplication and division are opposite from each other. How do I undo? What's the opposite of square root? An exponent. Okay, an exponent of 2 in this case. The way I'm going to undo a square root, I'm going to do squares to everything. So I'm going to do the squares to the sample. I'm going to do the square to my C-score. I'm going to do square to my standard deviation. And I'm going to do the square to my square root. But I know a square root and a square cancel each other out. So that gives me that my sample error all squared. So SE, it's a number, my sample error all squared. It is equal to my C-scored squared times my sigma squared divided by n. Cool. Again, I'm trying to come up with a formula where I have n by itself because I want a formula that I can use to be able to solve for my sample. And remember, n is my sample. Okay, so let me just multiply it. I don't know if most of you like fractions, but let me get rid of fractions. Let me multiply both sides by n because I want these n's to cancel out. I don't want fractions. So that means that I have, let me use in blue, I have n times the sample error squared is equal to my C-scored squared times my sigma squared, standard deviation squared. One more step, one step and I get there. But as a matter of fact, my next step, I'm gonna write it here on our formula. I'm gonna use red. I think I'm ready for my formula. Let me zoom in. I think you guys can come up with it over here. Let's assume everything are numbers. Right? Standard error is a numbered. My C-scored is a numbered. My standard deviation is a numbered. N is the only one that is not. How do I get N by itself? I see where N is, and I see I'm multiplying it with my standard error. Okay, so how do I do my N by itself? And let me write it here, because I want my formula. I want to write a formula such that N equals something. Okay, some of you might be able to see it. Good, so I'm just gonna divide. Let me divide both sides by my standard error squared. So that's gonna give me my C-scored all squared times my standard deviation all squared divided by my standard error squared. I know we're statistics students, so we can follow this. This is just an algebra step, right? I divided by the standard error squared. So I'm going to use this formula. So it seems like I need my C-scored, my standard deviation, and my standard error. And then I'll be able to solve for my sample. How big is my sample? So let's take a look. If you wish to estimate a population mean with the sampling distribution error of 0.24. Let me write some information here. Sample error is 0.24. Using a 95% confidence interval. Okay, my 95% confidence interval gives me a C-score. According to a table that we saw last week, my C-score for a 95% confidence interval is 1.96. And you know from prior sampling that the standard deviation squared is approximately 7.4. My standard deviation squared is 7.4. Keep in mind, let me just emphasize, my sample error is not squared. 0.24 is not squared. My C-scored is not squared, but my standard deviation here is. Okay. How many observations will have to be included in your sample? So let me do this. I'm going to go my N. My sample is going to be 1.96 squared times 7.4. All of this divided by 0.24 squared. Some of you might be wondering, why is 7.4 not squared? Do you know? Why 7.4 not squared? Yeah, because it was already here, sigma squared. So I'm going to type this in on my calculator. Again, if you need help on how to type this in, do let me know. According to my calculator, I get about 493.5 and then some more. Okay, now let me ask you this. According to my formula, this is the minimum that I need. I need 493.5 people. This is my sample. I need 493.5 people. If I get less than this, my sample might not be good enough. My answers will not be good enough. If I get more than 493.5, I'm good. But less than 493.5 is not good. Now, can I get 0.5 people? Can I get decimals? Not necessarily, right? So my answer is either 493 people or 494. Let me just write that here. So this answer either gives me 493 people or 494. I cannot do decimal people. I cannot do half a person. I know as a joke, we say sometimes a person that is here physically but not mentally is half a person. We say that as a joke, but really we cannot do half a person. But remember how I just said a few seconds ago, if I get less than 493.5, my data might not be correct. So if I get less than 493.5, my data is not correct. So guess what? I cannot get 493. I'm not going to round my numbers how we usually do it. Like, if the decimal is 5 or more, we round it up. If it's 4 or less, we round it down. No, 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 no. We're always going to round up, no matter what. So in my case, I'm going to have 494 people. I cannot do halves, but I cannot do less than 493.5. 493.5, I have to round it. So some of you might be wondering, Mr. Alonso, what if I type this in 483.1? Is this 493 or 494? And I will say that also rounds up to 494. You cannot round down. Because remember, if you get this, again, this is if you're doing another example and you get this, what that thing says, less than 493.1 is not good enough. So 493, not good enough. That number would also round up to 494. Like I said, in this case, we are rounding up. Okay, let's take a look at this other sample here, another thing here. In a sample of 17 specimens, the research found that the mean and standard deviation of the amount of radioactive element, cesium-137, now even though it has a number, this is just an element, okay? That was present to be 0.009 and 0.004 microcurie per millimeter respectively. Okay, respectively. So this it means these numbers came in an order. This is the first one, this is the second one. Let me go back and read this. Researchers found that the mean and standard deviation. Ooh, okay. So I'm just gonna say the mean. My sample is 0.009. My standard deviation, I'm going to call this S. My standard deviation is 0.004. Some of a fact inside here, let me just say it. My standard deviation could be sigma. We use sigma when we're looking at population. We use S when we're looking at sample, but we can use one or the other. Now, suppose that researchers want to increase the sample size in order to estimate the mean to be within 0.001 from its true value. Okay, so I want to be within. Okay, I don't want to be more than 0.001. Oh, so that means my sample error, the maximum sample error that I can use is 0.01. Using a 95% confidence interval. Ooh, my C-score. My C value for a 95% interval, according to my table from last week, my C-score is 1.96. Compute the sample size necessary to obtain the desired estimate. Okay, so I remember my formula. Let me rewrite my formula. My N, for me to know my sample size, I have to go my C-score squared times sigma, standard deviation. I could use sigma or S, standard deviation squared, divided by my sample error square. Seems like I am not going to need my average. Okay, I think I got this. We have the information here. For my N value, I'm going to go 1.96 squared. My standard deviation is 0.004 squared. And I'm going to divide this by 0.001 squared. Okay, so I have to type this in, right? It's not that bad. According to my calculator, I get 61.46. Okay, but we cannot have decimals, right? My sample has to be a whole number. So less than 61.46 is not good. So I'm gonna say in this case, because remember I have to round up, my answer is 62. We're not following the rules that we do for the rounding, right? This will round to 61. The nearest whole number is 61, but I cannot have less than 61.46. So I have to go with 62 people. My sample size must be at least 62. The bigger my sample size, the closer I am to the actual value. But here, my sample size must be at least 62. Okay, now a study of a lobster trap placement used a 99% confidence interval. Okay, let me see my information that I'm getting so far. 99% confidence interval, that means I have a C-score. According to our table from last week, our 99% confidence interval, my C-score is 2.575. Right, that's my 99% confidence interval. To estimate the mean trap spacing in meters for a population of red spiny lobster fishermen fishing in the West Coast. How many teams of fishermen would be needed to be sampled in order to reduce the width of the confidence interval to 5 meters? Oh, okay. Now this is interesting. The width of the confidence interval. Remember how my confidence interval is 2 values? Remember I get, let's just say there's x prime plus the standard error, and then there's x prime minus the standard error. That's how I get my 2 values, right? But in this case, it's telling me the width. So from the smallest value to the biggest value, my width is 5 meters. So from the smallest value to the biggest value, 5 meters. But wouldn't my standard error only be half of that? Good. So yeah, it is half, right? Because there's my X crossbar in the center. So I'm gonna say my standard error in this case is 5 divided by 2. So my standard error is gonna be 2.5. Okay, let me erase this. Okay, assume prior knowledge indicates that the trap spacing readings for the population of red spiny lobsters taken during the day are approximately normally distributed with a standard deviation. Ooh, okay. My standard deviation. Now, my standard deviation is that S or S squared? It's just S, right? Okay, so my standard deviation to be 11.9. Okay, we're looking for the sample, right? Because I see the question, it asks how many teams of fishermen will be needed. So yeah, we need our N. And besides, that is our work for today, so it's not hard to do. So I know I have to do my N according to a formula that I gave you guys at the beginning of the lecture. It's going to be our C-score value squared. So I have to go 2.575 squared times our standard deviation squared. So times 2.5 squared. Divide this by standard error. Oh, so no. Here is our standard deviation. The standard deviation is 11.9. My bad. I have to divide this by a standard error squared. So I have to divide this by 2.5 squared. According to my calculator, I get 150.23. Okay, so what's my answer, guys? I cannot have decimals. If I use the regular rounding rules, it's 150. So 150.23, the closest whole number is 150. However, my minimum is 150.23. Anything less than that is not good. So my answer in this case will be 151. Now we're going to use a formula. We're going to look at a last example here. Our formula for sample size given, our percentage. So basically, I gave you your P prime, your P hat. We're going to say, the formula I'm going to use for this, let me use black for this thing. My sample size is going to be my C scored squared. At the bottom, let me do a big fraction. At the bottom, I'm still going to have my sample error squared. Now, my problem here is that I'm not going to have standard deviation. I'm only going to have the probability of success, or P hat we called. Now, that one's going to be, I'm going to multiply this P hat times Q hat. Not squared, just P times Q. And my standard error, we'll be able to find standard error. Let's take a look at here. One example here, a 95% confidence interval. So 95% confidence interval, that gives me a C score. According to our table from last week, the 95% confidence interval, the C score is 1.96. So 95% confidence interval for P is given as, and then it gives us a space, right? It gives us an interval. How large was the sample used to construct this interval? Okay, so first of all, I need to find what's P. I know P is a number that is in between these two values. So what number is right in between 0.45 and 0.75? Like right in the middle, do we know? What's the number that is right in between those? Probably we cannot see it, right? Okay, so what I'm gonna do to find what's in between them, I'm gonna do the average of these two numbers. So I'm gonna go 0.45 plus 0.75, and I'm gonna divide this by 2. So does that give me 0.6? Okay, so I know my P hat. I know the probability of success. 0.6 is a number in between 0.45 and 0.75. From there, I can figure out the probability of failure. Isn't it 1 minus P hat? So in this case, 1 minus 0.6. So I'm going to say is 0.4. But I need my standard error. That's not bad. That's not hard. Let's find this out. My standard error, the way I'm going to find my standard error is going to be my P hat, the number in between, minus the lower value. So 0.45. My standard error is my P hat minus my lower interval, my lower value in the interval. I know P hat is 0.6. 0.6 minus 0.45. It's going to give me my standard error is 0.15. So remember, the standard error is how far off are you allowed to go from the average, from the center. So 0.6 minus the low value. Now, some of you like, could have I used the 0.75? Yeah, 0.75, that in this case, 0.75 minus 0.6. Okay, so I think I have enough. I have enough for my formula. Using the formula I just gave you right above there, I still see it in black. I'm going to use my sample that I need is going to be 1.96 squared times 0.6 times 0.4 divided by 0.15 squared. So this gives me like 40.98 or so. Okay. Again, I cannot have decimals because on a sample, I cannot cut a person in parts. So I have to have a whole number, but it cannot be less than 40.98. So my answer in this case will be 41. And that's what we did.